Welcome back. This is Larry Benko W0QE, and this video is a continuation of the previous video, but will be specifically about transmission line reflections at the transmitter or amplifier end of the circuit. This topic is periodically discussed in amateur radio, with all types of claims made as to what happens to the reflected wave into the transmitter, but I've never seen anyone publish measurements and how they were made. Also, this is my first time making these types of measurements, and if you have a recommendation as to a better approach, please speak up. The process of trying to figure out how to make a measurement of the return loss of a transmitter while it is actually transmitting, or maybe not transmitting too, I'd like to make both measurements, was kind of an interesting process. There were two things that initially occurred to me. I could use the transmitter itself as the source for the reflection, which is what the transmitter does itself, or I could possibly use another generating device while the transmitter was still transmitting, or this is what you would have to use if the transmitter wasn't transmitting. You'd have to use another device to be able to make this measurement. And I wanted to do this without the microprocessor that's in just about every transmitter made, not messing with the output. Most microprocessors and transmitters are set to some limit. It might be SWR, reflected power. Usually it's reflected power, but I don't want the microprocessor messing with it. In most of the radios I have, the microprocessor also is involved with the initial waveform, and there's some leveling that takes place with the output, adjusting the power of the output slightly in the first fraction of a second. And I don't want this to mess with the results either. So I thought about doing things like a transmitter pulse test, which I indicated in the previous video. That was ruled out because of the length of the transmission line was involved. Plus, I didn't want to make the measurement in the absence of when it was transmitting only. This is nice if you want to do that because you send a burst and you wait for it to come back, but by that time the transmitter stopped transmitting. I have no idea whether the transmitter will have the same reflection coefficient when it's transmitting or not transmitting. Some kind of delay network, again, is ruled out because the number of components and the complexity is just ridiculous. Time domain reflectometer. I don't really want to sweep the reflection coefficient from a transmitter. I just want to know what it is at a particular frequency where it's set to transmit, or at some frequency very, very close to that. I really could care less if a transmitter is transmitting on 40 meters. I could care less what the reflection coefficient is on 15 meters. It just doesn't matter. During this discussion, I may use terms like reflection coefficient, return loss, and SWR all interchangeably. And this little table here shows the three of those are all tied together with formulas. I've gone through this before, but they all mean the same thing. Each one is just a different way of describing the same process. So I'll try to use reflection coefficient mostly, but then I thought about perhaps a continuous transmission from the transmitter with a directional coupler. And that would be something like this. We've got the transmitter under test. We have a directional coupler in here that I showed how it worked in the last video. We have a load out here. This load is not a 50 ohm load, and ignore the X for the moment. It's not a 50 ohm load, but it allows some amount of signal to come out here and a percentage of it to go back. We can measure the forward signal down here with a scope or with a spectrum analyzer, and we can measure the signal coming back this way. I put 10 dB pads in the output of this directional coupler because I didn't want the input to my scope being above 1 watt, and I didn't want the input to my spectrum analyzer being above 1 watt. So I need an extra 10 dB pad here. But nevertheless, if I do this, the measurement we're trying to make is the transmitter is transmitting, and we've got a signal that goes out here, comes back. Something happens to it when it comes back. It either gets re-reflected back, it gets consumed in the transmitter, or something. But it's hard to see the presence of what comes back in the presence of the actual transmitted output. Now you can kind of do it, but it's hard to do it accurately. And after messing with this a little bit, all I could see was only really, really huge reflections. If the reflections were small, they were swamped by the transmitter. And plus, doing it in a continuous state, I had no idea if the microprocessor was getting involved. So I quickly decided that this was not really the plan I wanted to go on and looked for something better. I thought about a diplexer. A diplexer is kind of interesting. I can transmit and the transmitter output will go to some port that will have, like, say, a 50 ohm load on it, consuming the transmitter's output. And then the other port can be a slightly different frequency, and I can transmit back into the transmitter, and I can see a reflection that will occur at a different frequency. While that's very appealing, the Diplexer, unless you build it with incredibly high Q components, means that the two frequencies have to be separated fairly far in frequency, like maybe 10%. And at 10% separation, that means that the output adjustments in an amplifier or the whatever would perhaps be not really the same answer that I really wanted to see. I really wanted to see what the reflection coefficient would be at the transmitted frequency, or very, very close to it. Then I thought about a directional coupler with a second transmitter. And that looks like this drawing. So I transmit on frequency 1 out of my transmitter. I go through a directional coupler. I have a pad here because I got another transmitter that's tied to the output of this transmitter. I have to make sure that I transmit when this one and this one are transmitting. Before I put them in the transmit mode, but before I put the power to either one of them, I have to both have them in the transmit mode so that I don't transmit into the receiver of the other one. But that's not very hard to do. You can do it with a little switch, and I made a little sequencer to do that. So I would key them both up to be in the transmit mode, and then I would turn the power on to them separately. But in this case, I transmit at frequency 1. This signal goes into this pad. This pad is a 20 dB pad. It basically is a dummy load also for this transmitter. And I could transmit out of here at 100 watts if I want, and that I get a small signal back here that's a different frequency. Now, if I put a spectrum analyzer on here, I see a forward wave that comes out here at frequency 1. I also see the reflected wave that comes back here at frequency 2. Part of it gets re-reflected back here and comes down here, and I see it as frequency 2. Now, when I do this, I get some intermodulation distortion on the transmitter output, but it wasn't enough to really affect the results more than it was less than a dB difference. So this way worked, and this is what I actually ended up using. And it worked pretty nicely. And if I wanted to calibrate this for the reflected power, I could just open or short this point right here. I would get 100% reflection, and I could measure the level here at the spectrum analyzer for open and short, and then I could connect the transmitter back again and see how much weaker than the open or short reflection was with the transmitter. And if that's 5 dB better than the open or short, then I know I have 5 dB return loss on the transmitter's output. And I can convert that to a reflection coefficient if I want. But this worked pretty nicely. And I went with this, and I measured a few transmitters, and I'll get to those results in a little bit. But I thought as I was doing that, I thought about some other things. I lamented the fact that, once again, a circulator is not available at HF. They're available at VHF. But if there was one available, we could use something like that to make this measurement, and that'd be nice. The other thing is a load pool test. The load pool test is where you take a representative sample of impedances at a certain SWR, and you face the transmitter with those impedances, and you see that the transmitter produces the same power, or roughly at all the different impedances representing a certain SWR. And in industry, you use that. It's called a load pool test. It tells you whether the output of the transmitter is fairly symmetrical relative to 50 ohms. And while I could make a measurement like that, it really doesn't tell me what the reflection coefficient of the transmitter may be. Finally, it occurred to me I could perhaps do some kind of an impulse load change. That's back to the original picture again. But in this case, what I would do is I would start off with the transmitter transmitting here into a load. Let's say it's a 3-to-1 SW. Let's say it's a 1-to-1 SWR. It's a 50 ohm dummy load. But when I throw the switch here, it becomes like a 3-to-1 SWR. So the transmitter's transmitting its full 100 watts, or maybe 10 watts if I want to do a test at 10 watts. It's transmitting out here at that power level. I'm getting virtually no reflection coming back at all, because this is a good 50 ohm load. And then I very quickly do something out here. This would be tantamount to your antenna breaking a loose connection or something like that. And the transmitter may do something, but it's going to take it a millisecond or so to do it. In the meantime, to do that, I've had plenty of time to look at the signal here with the scope, and I can capture it. So try to follow this. Try to follow with this logic. I transmit here. I'm in a continuous state. 100 watts going out of this transmitter. I see a signal coming back here. It's very, very weak, indicating that very good load. I see my full power forward wave coming out here. I can see the phase of it very nicely on a scope. I throw this switch, and in the case of when I did this, it was a high power read relay. It dropped in under a millisecond. I could see on my scope instantly at the time it dropped an increase in reflected power, and I could see instantly a change in the forward power. By having the forward power signal right before this occurred and right after this, I could see the amplitude change and I could see the phase change in the signal going forward. And from that, I could calculate return loss. I almost like this scheme best, although it was a little tricky to build this up, and I needed a scope that had enough memory. So remember, I'm capturing this all the time. I start the trigger when I release the relay, so I need to trigger for at least a couple milliseconds at a pretty high sample rate to see everything that's going on. Scope I have has got 14 megapoints of storage, which is plenty to get several milliseconds worth of delay at still at a say a 20 nanosecond or 10 nanosecond per division sweep rate. So this was another way of doing it. Both of these ways seem to work well. I got similar answers on both ways. And I'm not so sure that both of these have a fault to them. The fault with doing it this way is that the second frequency I'm putting into the transmitter really isn't the same as the output frequency. And because of that, you might argue that that's not correct. It has an interesting characteristic doing this, is that I see all the phases. Because if the two frequencies are different, as the one frequency and the other frequency go through time, I see every phase of the reflected signal relative to the transmitted signal occurring. And it occurs, when I did this with a 20 kilohertz spacing, and they occur in 25 microseconds. Half the difference in frequency. If the difference in frequency is 20 kilohertz, that's 50 microseconds, and in 25 microseconds, you run through all the phases. So I can look at this and see the results of all the different phases at a certain, the certain reflected power coming into the transmitter if I wanted to. This one, I can't do that. I have to do each load independently. But this one gives me the ability to guarantee that I'm measuring it at the right frequency. Again, if there's a better way to do this, these are the two best choices I could come up with. If there's a better way to do this, I'd be certainly willing to discuss this with anybody. Plus, if I'm off, if I'm way out in left field here, let me know. Again, we're trying to separate the transmitted or the amplifier's output frequency, output power, from the reflected signal. The signal goes out, comes back, and gets re-reflected at the transmitter or the amplifier. We're trying to separate those two so I can measure this one in the presence of this one. I'm going to require that it doesn't cost me a lot of money to buy some piece of equipment to do this too. I certainly don't mind building or buying something small, but this type of a measurement should be nice that more than one, more than somebody with a full lab can make. So, with this being the case, let's look at what let's look at the actual test setup. All right, here's the test configuration I used. Got two radios, ICOM 706, which is under test, and ICOM 7000, which I'm using as the reflected power generator. Got a watt meter, a 10 dB pad, which is 100 watts, another 10 dB pad here, or 9.8 dB pad, which is 1,000 watts. Directional coupler, and spectrum analyzer for this test. And if I turn on both generators, we can see that the scope shows some IMD being created. It also shows the forward power being the peak signal there, And the one just to the left of that is the reflected power coming back, well, not coming back. The reflected power is generated by the other generator. And this is the configuration I used in all cases, and the results are shown here. Two tests are shown here. One where I tested to 706, one I tested to 7,000. I tested, when I swapped the radios, I actually did two other radios after that. I did a K3 and an ICOM 756 too, but I didn't. The data is not shown here. What I did was two tests. I ran 100 watts here, which through the 20 dB pad gave me basically 1 watt here to put directly into the transmitter under test. And I ran 10 watts here, which put a tenth of a watt in. So that's the 1 watt and the tenth of a watt reflection category. Then I also, from this transmitter, I keyed it up with no RF power. I ran 10 watts and I ran 100 watts. So this line right here represents 10 watts at the transmitter under test with 1 watt coming in. That represents something in the order of like a 2-to-1 SWR. And I also made a measurement for short and open here at point A so that I knew what a 100% reflection would look like in terms of the signal strength here. These are the results. So when the transmitter, the 706, was keyed but with no RF present, based on the reflection magnitude, I saw between 3 and 3.4 dB of return loss. Then I saw between 5.1 dB when I was running 10 watts out of the 706, and I saw 10.2 and 9.3 dB of return loss based on the magnitude of reflection again when I was running 100 watts out of the 706. So 3.4 dB of return loss, or 3 dB of return loss, represents an SWR somewhere in the order of just about 6 to 1. A 5.1 dB return loss represents an SWR of about 3.5 to 1. And a 9 to 10 dB return loss represents an SWR of about 2 to 1, looking back into the transmitter while it's transmitting. Now the ICOM 7000 was a little bit different. It was a little bit better. It was about the same with no power output, but yet keyed. A little bit better at 10 watts, and somewhat better here. It was 12.9 and 13.8 dB, so it looked like somewhere between, maybe 1.6 and 1.5 to 1 SWR at full power looking back in. So bottom line here is, with 3 dB of return loss, that means half the signal stays here and half the signal comes back. That was the worst case. And in all the other cases, considerably more of the the reflected signal was dissipated in the transmitter. Did not return back on the line. So that's the data I collected. Analysis I did, which I'm not showing right now here in LT Spice, show that when the reflected signal is not returned back into the transmitter under test, it is dissipated in the resistive piece of that impedance that we see when we look in. And in all cases, this SWR, when the transmitter was actually transmitting, was better than 3.5 to 1. And when it was transmitting in full power, it was better than 2 to 1. So anyways, that's just the test. That's how I did them. Please critique what I did. I'm not an expert in this area. This was kind of a fun little test to do. And maybe you can get some people to pursue this a little bit further. Anyways, thank you very much again, and I've enjoyed this.